In this video, we're going to talk about the monotone convergence theorem for sequences. There are other monotone convergence theorems in analysis, for example, the one for integrals, but for now, we're going to be focusing only on the one for sequences. So let's get started. I have a question for you. So we showed that if I note that a sequence is convergent, then it is bounded. Is the converse true? That is, are bounded sequences always convergent? I hope you said no. We've seen already examples that will show us that is not true. And a typical counterexample is the sequence minus 1 to the n. Right? If you look at it, it goes like up and down, up and down, up and down. It oscillates, so it cannot just accumulate towards a limit. But now I want you to think about a bounded sequence that can only go up. Okay, so if it can only go up, imagine that you're just climbing up, and then eventually you hit a wall and you want to continue going up. But the wall will not let you go. So you will have to stop at that point, so you will converge toward that limit, that wall. Okay, so here I have a picture that will help us see this. Well, it's bounded, and I have an upper bound m. We can see that all the points are going up. And if you look at it, it doesn't seem to be convergent to that m, right? It's not getting very close to that yellow line. Okay, but m was just an upper bound that I picked, but there are many others. So what if I pick a smaller upper bound? And if you see this blue line, now the terms seem to be getting very, very close to that blue line. So they seem to be convergent to that value. And I would like you to pause for a second and try to think about what that blue line is representing. It is clear that it is an upper bound. But, well, it seems to be special. That's where all the points are accumulating. Can you think of a very special upper bound that could play this role here? Great. If you set the supremum, you are right. When we have a sequence, right, it's going up, and it's bounded at some point, you will just hit a wall, as I said, and that will just force it to converge to that limit. So it really seems that the sequence converges to the supremum. That's absolutely mind-blowing. Now we have a connection between bounded, increasing, because going up means increasing, so we have bounded, increasing, and supremum. They're all connected. And that is what the next theorem is going to tell me. That if I have a sequence that is increasing and bounded above, then my sequence is convergent. So let's see. We want to show that the sequence is convergent. That means that I want to show that the sequence converges to L for some L. The theorem is not telling me what L is. It's just telling me that it converges to L for some L. We just need to find what that L is. That's going to be the main thing here. So here, what we want to show, I'm writing it down, like everything like really like displayed with all the quantifiers. We want to show that for there exists a limit, right? So we want to show that there exists an L such that for every epsilon, there exists an n naught such that after that point, all the terms an are within epsilon of L. So like an is between L minus epsilon and L plus epsilon. And here I put that in yellow because that is something that students tend to forget. When we want to show that something converges, we need to show that there exists a limit. So there exists an L. Now, this has lots and lots and lots and lots of quantifiers, so it's quite tricky to prove. So let's try to break it down and let's try to come up with a plan. So based on the definition, what is the definition telling me with respect to the proof? Once I have the structure of the proof, we're going to try to kind of come up with the right ideas, and then we're going to write a nice, clean, polished proof. But first, let's focus on the structure. It tells me there exists an L. Well, I just need to pick an L that will work. That's the hard part, it has to work. But we'll have to guess this one, right? We have to find an L that will make everything work. Then, well, we need to pick an arbitrary epsilon, right? Any positive number in the world could be epsilon, so we pick an arbitrary epsilon, we fix it. Now, for that choice of epsilon, we need to choose an n naught. Good. And now, after that, we're going to assume that I have an n bigger than n naught, and we have to conclude that then an is between L minus epsilon and L plus epsilon. So let's try to first, as I said, come up with the main ideas, and after we have all the main ideas, we'll put everything together. So main ideas. We're going to define a set S that has, well, all the terms of my sequence. If you look at it, the set is not empty, right? Because you have infinitely many terms. Unless, well, the sequence is constant. In that case, it will be a finite number of terms, but we know it's definitely not empty. A1 is in it. And then we know that it's bounded above because my sequence is bounded above. Well, that tells me that the supremum exists. Well, why? You might ask. Well, because the completeness axiom tells me that if I have a non-empty set that is bounded above, then it has a supremum. Very good. And here, well, we go back to a picture that we had at the start of the conversation. And then what I'm going to do is I'm going to take L to be the supremum of this set S. And what we'll show is that indeed my sequence converges to L. Okay, how can we do that? Well, for any epsilon that I pick, I know that L minus epsilon is not an upper bound. Why? Well, if you remember, the definition of supremum says that the supremum is the smallest upper bound. So any number smaller than L cannot be an upper bound, and L minus epsilon is less than L. So we know that L minus epsilon is not an upper bound. And that means that I can find an element in my sequence that is bigger than L minus epsilon. Very good. We seem to be going in the right direction. Then I know that my sequence is increasing. That means that all the terms after this A naught that I just picked are going to be bigger than A naught. Okay, so then in particular, I know that for every n bigger than n naught, L minus epsilon is less than an. Oh, that's looking pretty good. It's promising. And now I know that L is an upper bound. So all the terms have to be less than or equal to L. But L is less than L plus epsilon. And then that is going to allow me to put all these inequalities together to get the result that I want. So let's see, how can we write the proof? Well, we begin by saying, well, we have a sequence that is increasing and bounded above. Good. And we're going to define the set S that I already talked to you about. And we're going to say, well, this set is not empty and bounded above because the sequence is bounded above. Okay. Therefore, by the completeness axiom, the supremum exists. And we're going to take L is equal to the supremum. We're just giving it a name to make our life a bit easier. And we will show that An converges to L. Okay. We need to fix an epsilon positive, and we need to find what that n naught has to be. But you see, by the definition of supremum, there exists an n naught such that L minus epsilon is less than a n naught. We already discussed why. Okay, very good. But now we're going to assume that n is bigger than n naught. Since the sequence is increasing, then what happens is that an is bigger than an naught. And now, because L is an upper bound, we also know that an is less than or equal to L. Now, if we combine all these, we get that L minus epsilon is less than a naught, but a naught is less than or equal to an, but an is less than or equal to L, but L is less than L plus epsilon. So when we put everything together into a nice, beautiful absolute value, we end up with the absolute value of an minus L is less than epsilon, and that completes the proof. Okay, now there is another two theorems. The first one I'm going to talk about is, well, if I know that the sequence is decreasing and bounded below, then the sequence is convergent. Can you think of what the limit should be in this case? Try to think about that. And now if we combine the one that we proved about increasing unbounded above and the one about decreasing unbounded below, we obtain the monotone convergence theorem for sequences, and tells me that if I know that a sequence is monotone and bounded, then the sequence is convergent. Once you prove the first two ones that I talked about in this video, the other one will be quite easy to prove, and I will leave for you as an exercise to complete the proof of these two theorems.